A question of tolerance, getting what you want. Last time we talked about tolerance, and here's a short recap. Tolerance is when you say give or take, plus or minus. Usually the amount is given in percentages, but you can convert it into a range pretty easily. So whether someone's selling you zener diodes at 5.6 volts or saying people on Green Island are 5 foot 6 inches tall, or thereabouts, you understand that there's no guarantee that if you buy a zener diode it's 5.6 volts exactly, or that anybody on Green Island is 5 foot 6. Here's the mathematical version written out. 5.6 plus or minus 5% is 5.3 to 5.9. It's a range. People on Green Island can be any height. It's a range of heights. They don't have to be 5 foot 6. You can still correctly say people there are 5 foot 6, give or take. I went through more than 40 zener diodes and never found one that was exactly 5.6 volts, even though they were advertised as 5.6 volts. That's because of the tolerance, because there's a range of values they can be. And we concluded that if you use the term range instead of tolerance, it makes a lot more intuitive sense. And you understand that if you buy something within the range of 5.3 to 5.9, you don't have to get a certain value. Getting exactly 5.6 is just as likely or unlikely as getting 5.9. Really? That doesn't make sense, though. Well, it's like saying you're just as likely if you spin a wheel 10 times to get all bankruptcies than to get 600, 700, 900. You're saying that even if you spin the wheel a million times, you may never hit the trip to Italy? It depends. If you look at casinos, you could play this slot machine a million times and never win. We all know that. Many people literally play it thousands of times, if not more. Just go to one of those smaller towns, those Indian reservations, where the casino still allows smoking, and you see all those old people sitting there playing it all day long, literally. I think we all understand this concept if it's based on a casino. It seems like it's random. The numbers roll after every spin. If you play long enough, you should get exact one you want, right? The three cherries. But we all know that it's not true. It's not exactly random. Because the wins are not distributed in that way. Wait, what does this mean? Well, let's take a look at some distributions. Some distributions in real life, like the fires here in the Bay Area. If you notice, they're not evenly distributed, as in they're not every 100 miles, for example. There's some places where there's a cluster of fires, and some places there are no fires. Like the Mojave Desert, there's nothing to burn there. It's really hot. Death Valley broke the record recently at 135 degrees or something. But what are you going to burn? Nothing. It's sand. The places where there are fires have lots of brush, lots of trees to burn. Houses themselves, if it's just a gigantic subdivision like LA or Southern California, they're actually really hard to burn. They're actually meant to not be burned. That's how they're built. Even if lightning were to strike directly one house, it most likely won't burn up, and even if it does, it doesn't mean it'll burn up its neighbor. You need a lot of shrubbery, a lot of trees to really get a fire going. So it makes sense that fires aren't evenly distributed because trees aren't evenly distributed. We could guess where there'll be fires, where there won't be fires, like in the ocean. And even if we wait till next year, and the year after that, and the year after that, it seems that some places will just never burn, and some places will keep on burning, as we see. If you look at a distribution of height here of people across the world, you'll see that most men are 5'10", most women are 5'5", meaning that it's likely to find a woman who is 5'5", more likely than a woman who's not. And when you get really tall or short, it's very unlikely, and we see that in real life. We don't see very many tall people. Say people who are 6'6", 7 feet, they're very rare. People who are very short, not 5 feet, that's also very rare. The shape of this graph, which goes up in the middle really high, is the most common, most prevalent in the middle, and then down on both sides like a hill, is called a bell-shaped curve. You could picture it looking like a bell. It's also known as the normal distribution, the standard distribution, the most popular one in statistics. And here it is from a math site. You see how the highest percentage of people or numbers is clustered right in the middle. As you go farther out, there are less and less people or numbers in that range. This is what people think about when you talk about a range. They presume your numbers are distributed evenly. But when we say evenly, we don't mean literally evenly, but we mean in this way. They say this is the normal distribution, the way found in nature. But if you go back to this made-up green island, we look at people's heights, and if I classify them, you can see people's heights aren't distributed like a bell-shaped curve. They're not evenly distributed at all by any measure of that word, evenly. And if we add more people, there may still not be somebody who's 5'6". And if you keep adding people, there may still never be a person who's 5'6". Maybe there's a rule on Green Island that nobody is ever 5'6". But the range of heights is 5'3" to 5'9". And if we replace people with diodes, and instead of 5'6", we say 5.6 volts, you can see that there may not be any diodes that are 5.6 volts exactly, even though the specification is 5.6 volts, give or take 5%. This is actually what I found. There were none in the 50 diodes I checked that were exactly 5.6 volts. 0. And that makes sense because there are many types of distributions. As many types of distributions as there are types of people or colors of crayons, or ways to combine words and instruments into music. Before I learned this lesson, I thought I could just keep on trying, keep buying more diodes, and I'll eventually find one that's 5.6 volts exactly. Or you may think when you go to Green Island and you wander around that you'll find somebody who's 5.6 exactly the same height as you are. But after wandering for hours and finally days and months, you realize, wait a minute, there's nobody who's 5'6". So I think we realize the statement has to be modified because your success depends on the distribution. So if at first you don't succeed, presuming normal distribution, try, and try again.